We're looking at problem number 17 from the test review, number 5, test 5 review. We're going to go through the steps on how you can factor a problem like this, where traditional factoring methods like grouping and guess and check don't really work that well or at all. So every time you're looking at a problem, you should first check if you can factor it. Some of the ones on the test review and the test will be factorable, and that's a much quicker process. If I can't use traditional factoring methods, then I'm using the rational root theorem to find some roots and to factor at the same time. So it's just a secondary, or I guess a third technique that you can add to your list of ways that you know how to factor. To do that, we need to first find the potential roots or possible roots. And that's the list of all numbers made up of the factors of your constant divided by the factors of your first coefficient. This would represent P and this represents Q. So this is P and this is Q. Except P is really a list of factors, not just that one number. So first I need to factor each of these. 39, of course we've got 1 and 39. Divisible by 3. Oh, that might be it, and I made a really long space. Yep. And then Q, since that's a 1 up front, Q can only be divided by 1 and -1. It is possible for this to have a number up here, so you might have a list of Q's as well. Next, to find the potential roots, we're going to divide each P by each of the Q's. So in this case, that's not much work because the Q's are just 1, but sometimes you might have other numbers down here, so you'll have some fractions. In this case, if I divide each of these by 1, it's just the number itself. So my list of potential roots is 1, 3, 13, and 39. Okay. Now what that means is that if your equation has any rational roots, then it's on this list. It's possible that it has roots that aren't on this list if they're not rational, meaning irrational like square root of 2 is, or pi, or it could be imaginary like I, or any coefficient of I. So it is possible that you have some not on this list. It only works up to a certain point. The next step is to see whether, or see which one of these is actually a root. There's a couple of ways that you can do this, but each method has its own benefits. One way, according to the remainder theorem, is that we could plug in the number that we're testing into the function and see what the y value is. If the y value is 0, then that means that this is a 0. If it comes out with any other number, then it's just a point on the graph and it's not actually a 0, so it doesn't help us to factor. The downside to plugging things in like this is that in the end, all you'll find out is yes or no, it is or it is not a 0. It does not help us to factor necessarily because you don't find out what the other factor is, what's left over after I've taken away that 0. So let's just look at one real quick. 1 minus 9, 31, 39. So if I combine these, that's -8. This is not going to be 0. This is more negative than it is positive. Let me try one that I know will work. This also isn't necessarily the best method whenever you've got really big coefficients like this, because as you can see, I'm doing some pretty large multiplication here. Let's see. I'm just going to grab a calculator to save us some time. Yep, this does come out to be 0. So as you can see, I'm able now to conclude that 3 is a 0. Which does tell me that x minus 3 is going to be a part of the factored form for this polynomial p of x. But the downside to using this technique is that I don't know what the rest of the factors are. So I'd still have to work to find that using synthetic division or long division. So I prefer to just start with synthetic division because it tells me both whether this is a 0 and also what's left over if it is at the same time. So I'm going to go back and do that. Now that I know that 3 is a 0, I'm gonna go ahead and do 3 with synthetic division. One thing to be very careful with synthetic is that if you're missing any powers, you have to put a 0 in its place. Thankfully, we're not missing any powers, so my coefficients are all I need for the top row of synthetic. That's 13. Cool. So that remainder is the same thing that I got as my y value, which is what the remainder theorem tells you happens, but I have an added benefit. I know that this is a 0, and I know that this is the leftover factor, it's the quotient. So when I divided this by x minus 3, I was left with this, which means x minus 3 is one of the factors, and x squared minus 6x plus 13 is the other factor. What that means is that if I were to multiply these together, it would give me back p of x that I had originally. So this is the same equation, but written in factored form. To find the rest of the zeros, I would need to split this apart or solve it by any techniques that I've learned in algebra. Now, I do not, very strongly do not recommend that you continue to test using the rational root theorem, because if the zeros for this factor have I, are imaginary, or have a square root, are irrational, this theorem will not find them. And you could test the rest of this list and never have a successful test. And that could happen if these are your other zeros. So I strongly recommend that you do not continue to test once you've got a quadratic. I know other ways to solve this without using the rational root theorem. All right, so the techniques that you've learned in the past for solving this would be, you could factor it, potentially. If this is factorable, that's also much quicker than trying to do synthetic division and test. If it's not factorable, you can use quadratic formula, because the whole purpose of quadratic formula is to find x values that make that quadratic function equal to 0, which is what we're looking for. Or you can complete the square. Completing the square also solves if you set it equal to 0 first. I'm going to demonstrate completing the square because I feel like it's something that we might not be the strongest at, and quadratic formula just requires you to know the formula and plug numbers in. So you can use either one, you should get the same answer. If you want to try quadratic formula while I do this, you can check your answer. For completing the square, the important thing to know is that we are setting the factor equal to 0, because what I care about is where or what x values create a 0. That's why they're called zeros. So I'm going to make it equal to 0 and then work backwards and solve for the x. For completing the square, I like to move any constants to the other side first, just so that they don't interfere with the work I'm about to do. That's totally optional, and I know some teachers don't teach it that way, so you don't have to do that. Next, I'm looking for what number could go here that would make a perfect square trinomial. And to do that, we take our b value, divide it by 2, and then square that number. So that gives me -3 squared, which is +9. So I'm going to add a 9 here to create a perfect square trinomial. Whatever you do to one side, you have to do to the other. All right, now we keep working. This side will now factor perfectly because that's what we did. We made it so that it would factor, and it always factors into the square root of the first number, the square root of the last number, and the sign from the middle. And then on the other side, we have -4. Now I can just square root both sides and my answer will appear. So if I square root, my marker's dying, and square root and plus minus because I did the square rooting myself. Square root of -4 is I square root of 4, which is 2, and then move the 3 over. You can also write this as 2 separate answers. If that makes it more clear that you've got 2 solutions there, that will help. So it looks like all in all, from the beginning all the way through the end, the first 0 we found was rational, 3, and then we used other techniques that we've done in the past to find the other 2 zeros. These would never have shown up in your rational root theorem because they're complex. They've got an imaginary part which makes them not rational. So these are the 3 zeros that came from this p of x. It can be used to graph it, or you can even finish writing it in factored form using your zeros. Let's do that now. All right, so again, my 3 zeros were 3 plus 2i, and 3 minus 2i. To write it in factored form, I'm just gonna take each of these zeros and fit it into a factor of this form, x minus whatever the 0 is. So this first one will be x minus 3. The second one is x minus 3 plus 2i. And the third one is x minus 3 minus 2i. The last thing I can do is distribute the negative. And if you're watching this and you're not in my class, it is possible that your teacher will not want you to write out these linear factors. So to do that, you would actually just leave it in the factored form that we had right before we completed the square, which unfortunately I don't remember now, so you may have to go back in the video. The factored form we had right before I looked for these complex zeros would be the factored form you could leave this in if your teacher doesn't want the i's in your factored form. But this is how you could completely factor it into only linear factors. And again, to check your work, if you multiply all of these together, it must equal p of x because we have been working with the same function, rewriting it in a factored form, not changing it to a different function. Thanks.